we have been working on calculating equilibrium constants, then using equilibrium constants to predict how chemical reactions will develop, how they will reach equilibrium, and calculating equilibrium concentrations. Okay? So that primarily involves a couple of things. One, we have to get some information about a system that's already at equilibrium. We need to know the equilibrium concentrations so that we can go through and use those to calculate K. Then we would take K and some new initial conditions and calculate how much, what will happen over the course of the reaction until we get to equilibrium, and calculate a new set of equilibrium conditions. So, I've been giving you those first pieces of information, the equilibrium concentration of a chemical reaction. But we need to be able to go through and do that work experimentally. We've got to be able to go through and determine the concentration of a solution after it's reached equilibrium. And we don't want to do it by changing it. We have to be able to go into the lab, set up an experiment, have it run, let it wait, it'll reach equilibrium, and we need to measure the concentration of the stuff inside that chemical reaction. One of the most common ways to do that, to measure the concentration of something in situ, in place, is to look at how it absorbs light. Okay? So we have a chemical reaction. It produces a substance that looks like this pale yellow color. Okay? Our basic plan is to take a light bulb, okay, and use the light bulb to shine some light through the sample. What's going to happen if I shine some yellow light through this sample? It will get absorbed. Okay, or I can choose a particular color of light that this sample will absorb. We'll talk about that in a little bit. But what's going to happen is I shine the light through this sample, it's going to absorb some of the light, so that the light coming out will be less. It won't be as bright. The difference between the amount of light I put in and the amount of light that I get out is directly proportional to the concentration of the chemicals that were absorbing the light. Okay? So we can use that relationship to develop a mathematical relationship known as the Beer-Lambert Law. Okay? So we have a beam of light entering into a sample chamber. Okay? As the light travels through that sample chamber, some of it is absorbed. And so the beam of light coming out is not as bright, not as intense. Okay? So this not quite as bright light coming out, the ratio between this light coming out and the light going in represents the amount of light absorbed. And we use a capital A for absorbance, the amount of light absorbed, and it's equal to the log of the initial light divided by the light that comes out. Okay? We're not going to calculate it this way. This is what our device, our tool, our instrument is going to do for us. The spectrophotometers that we're going to use are going to go ahead and they're going to run this little calculation electronically inside them. They're going to measure the light that they're shining onto the sample, and they're going to measure the light coming out of the sample. And I'll talk about how that works in a few minutes. And they're going to spit out the absorbance value. What we're interested in is how do the various factors of this sample cell change that absorbance value? Question?
What is light?
The light intensity is measured in candelas, but you never need to worry about that, because this is, since it's a ratio, it's a dimensionless quantity. So we measure the absorbance. It's the ratio of incident to exiting light. A is the absorbance. Capital A, absorbance. Little a, little b, little c are all factors related to the sample. Okay? Things that will affect how much light are absorbed are, how much of the sample does it have to travel through? what we call the path length. That's the length of the sample that the light travels through. We use lowercase b to represent that path length. You need to know all these values. There will be questions that say, tell me what A represents, what B represents, what C represents in the equations. So you got to make sure you know that. Okay? B represents the path length. That's the distance that the light travels through the sample. Okay? A, lowercase a in the equation, is going to represent the molar extinction coefficient, or the molar absorptivity coefficient. It's given two different names. And it represents how well, how efficiently does the sample, the chemical, absorb light of a particular color, of a particular wavelength. Okay? The light we shine through is going to be of a particular wavelength, and A represents how well does this chemical absorb at this wavelength. That's lowercase a. So C stands for the concentration. Okay? C is the concentration of the chemical we're trying to measure. So the relationship between the absorbance is that the absorbance is equal to A times B times C. So the molar absorptivity coefficient times the path length times the concentration is proportional to the absorbance, how much light gets absorbed. So A is the ratio of how much light did we shine on the sample to how much light came out. It represents what percentage of the light was absorbed. That's the capital A, absorbance. Lowercase a, so different samples, different chemicals at various wavelengths will absorb light more or less efficiently. So at a given wavelength, you could have a chemical that doesn't absorb light very well at all, and you could have a chemical that absorbs the light very well at that particular wavelength. And it has to do with the bonds inside the molecule, how the electrons are arranged, the energy levels, all kinds of factors like that will determine this molar absorptivity coefficient. Fortunately for us, most of the time we don't have to worry about any of that stuff. We typically use this relationship in a way where we're just going to relate the absorption to the concentration, because A and B are essentially fixed constant values, because we're talking about a particular chemical. So A is a fixed number at a given wavelength, and B, the path length, depends on our equipment, our piece of machinery, the little test tube, what we call a cuvette, that we use. Okay, and cuvettes are special optically clear test tubes made of special glass that has a low index of dispersion. It doesn't spread the light very well and stuff like that. So they look just like test tubes, except that they're a lot more expensive, and they are designed to be optically very clear. Questions? C is typically in molarity. Concentration of the chemical we're measuring. All right? So, yeah. Typically centimeters. But we're never going to need to worry about that. A is going to be, the units for A would be 1 over centimeters times molarity. You guys need to knock it off. Okay? If you don't want to pay attention, you know, that's up to you. But you have to not bug other people, including me. So, what we're typically going to do here is we're going to take this and we're going to build ourselves a relationship between absorbance and concentration, what we call a calibration curve. Okay? And the way we do that is by creating solutions, creating samples where we know what the concentration is. So I'm going to go through and I'm going to take the chemicals and I'm going to make a solution that have progressively higher concentrations. And I'm going to know exactly what those concentrations are because I made them. So I'm going to make these as accurately as I can to be known concentration values. And I'm going to take them, and what I'm going to do is I'm going to go ahead and I am going to put each of these samples into my spectrophotometer, and I'm going to use the spectrophotometer to measure the absorbance. So I'm going to know both the concentration and the absorbance for each of these known values. And all I need to do now is essentially plot those values. Okay? And over small concentration ranges, we should normally get a linear relationship. It's not technically a linear relationship, but if you look at small concentration changes, like from 0.1 to 1, so less, around at most a factor of 10 increase, it approximates a linear relationship, which makes our graphs much easier to work with. Because it does rely on the log of the ratio, over wide concentration ranges, it's actually a curve. Don't worry about that. For our purposes, we can assume that this should come out to be some sort of linear relationship, where the slope of this line would essentially be the combination of the molar absorptivity and the path length, those two values that are fixed. So the slope of this line would be related to the molar absorptivity and the path length. Okay, just that's what's going to determine this slope. What we're really interested in is the fact that we've now got a relationship between the absorbance that we can measure and the concentration of the chemical we're interested in. Now, this graph has to be produced at a particular wavelength. And we'll talk about how we choose that wavelength in a few minutes. But suffice it to say that we either have to figure out or be told what wavelength to use, and then we can go through and make up known concentrations, measure their absorbance, plot it on this chart. Now, the reason we're going to do that is because once I've got these known values plotted, I can take an unknown concentration. So I can make up a sample and not know what the concentration is inside here. And I can stick it into my spectrophotometer and measure the absorbance. So I don't know what the concentration is, but I measure the absorbance. Now I can come to the graph, I can measure that absorbance and say, all right, if my absorbance was 0.4, I can look on the graph and I can find out what the concentration is. Using the calibration curve allows me to take a solution of unknown concentration and measure its absorbance and use that absorbance to figure out what the concentration would be. Next. Technically, no. Over large concentration ranges, it won't be linear, but those are very difficult to use. Typically, we restrict ourselves to small concentration ranges where this graph approximates a linear relationship. We're only going to worry about linear relationships. All of our work will be for linear relationships. Yeah? You could determine the relationship, find the equation for the slope of that line, and do it that way. But typically, the way that they're going to do this on the AP test is expect you to do it by reading the graph. That's the way that they typically do these types of things. But you could go through and do the problem is that you have to go through and do a linear regression, which most people at this level are not very good at doing, to figure out what the equation for this line is. So most of the time, their answers are going to expect you to, you can do it that way, it's perfectly legit. Most of the time, they're going to expect you to do this and read the graph. That's what they expect. It depends on the situation. It depends on the piece of equipment you're using and what chemical you're measuring and what the wavelength is. Those are all constants, so they don't change. That's why it's the slope. But you can't say it's not the same for every situation. It depends completely on what chemical you're using, what your piece of equipment you're measuring it with, and what the wavelength you choose is. Okay? All right, so our big goal here is to be able to take solutions, create a standard curve, okay, to then use the standard that we create to determine the concentration of an unknown. That's the technique. That's how we're going to use the spectrophotometers. That's the most common use for this type of thing. It is super common to be used in scientific experimentation. Using this type of spectrophotometry to measure stuff is a really common way to measure the concentration of things. It's one of the things that I did last summer up at UC Berkeley when we were trying to measure the concentration of EDTA and different chemicals in wastewater and stuff like that. You separate it out using chromatography. Do you remember when we did the chromatography with the little columns and we pushed on the cylinders and different colors came out first? You hook the end of that column into a spectrophotometer, which then measures how much light is absorbed and tells you the concentration as the stuff is flowing through. That's really typical for how you do this kind of stuff. Separation on a column and then measuring on a spectrophotometer. There's obviously, we can use different wavelengths of light, we can choose different colors to help pick out just the stuff we're interested in, okay? And so, to give you a little bit of background on how all this works, and how do we choose what wavelength to use, we need to talk a little bit about how do the machines actually work, and what are sort of the parts of a spectrophotometer, what are the sort of important pieces. Okay, so what I have is first off a schematic of a spectrophotometer. Okay, so spectrophotometer, the heart of the spectrophotometer is the light source. We have a device that produces a broad spectrum of light. This is an example of a visible, we're using just essentially visible light. We take the visible light, the light source, a light bulb that produces a broad spectrum of light, and we put it into a device that will allow us to choose specific wavelengths, to choose specific colors of light, right? Color is going to coordinate with wavelength. The monochromator allows us to do that. It could be a prism, because when we shine the white light through a prism, it spreads the colors out. But it's much more likely to be a diffraction grating in a modern piece of equipment. By changing the angle of this, we can select different wavelengths of light, different colors of light. We send the wavelengths, we send the specific color of light, the specific wavelength of light through our sample. As it travels through the sample, some of it is absorbed, and we measure how much light made it through the sample using a photoresistor or a photodiode. There are different types of these devices, photomultiplier tubes, several different technologies that we use to convert the light into an electrical signal that we can amplify, and then we can run some calculations in the machine to spit out the absorbance. Okay? Fundamentally, the way that typically works is instead of there's a piece of the picture that's missing here, where we would have a mirror that would allow us some of the time the light to bounce around the sample. And if the light bounces around the sample, we can measure the initial amount. And some of the time the light travels through and we measure that, and the machine does the calculation based on the intensity of those two signals to spit out the absorbance. Yeah. What is it? You choose, what you do is you choose the wavelength, and then there's a technique, a process we have to do to set what we call the blank, or the 0 point. I'll talk about that in a sec. But in terms of the amount of light going through, no, that's built into the machine. It always produces the same amount. It produces a set amount of light. You do need to bounce it around because as you change the color, the intensity changes. Because this source doesn't actually put out the same intensity for all the different wavelengths. Yeah, they would, depending on the sample. That's why you're going to pick one wavelength to measure at. Well, I'll talk about it, it's an upcoming slide. Okay? So, I want to show you a picture of the spectrophotometers we're going to use. They're made by Milton Ray. They're called Spectronic 21Ds. This is a picture of the device that you're going to use. It's over there on the side of the room. We're going to have 4 or 5 of them in here. You're going to use it. I want to just point out the important parts of it so that when we talk about it tomorrow, you've had a chance to sort of look at it, okay? So, the most important pieces of this machine are the sample chamber. So you open this up and you can stick the cuvette, the special test tube, inside, and you close the top so no light gets in. You need to set the wavelength. There's a knob on the top with a readout in here where you can set what wavelength of light you're going to send through the sample. Okay? Across the very bottom of the machine, there are a couple of knobs that you might need to use. There's the power switch, no touchy. These things take 15 minutes or so to warm up to come to equilibrium. So we turn it on, we leave it on, we don't touch that. There's a sensitivity reading. If your concentration is very low, you can increase the sensitivity of the machine. That's going to increase the amplification of the signal. And then there's this last one, which is what we call our zero, or this knob is what we can use to set what's called set the blank. And this is all related to choosing a wavelength and understanding that there's some chemical we want to measure, and then there's everything else in the solution. And what we want to do is we want to make sure that our device, our spectrophotometer, is subtracting out everything else in the solution, how well it absorbs the color of light we're putting in. So this knob allows us to set how much should it subtract out of the values it reads. Okay? And so we'll talk a little bit more about that when we're working on this tomorrow. Yeah, Michael. Yes. This is based off of the original Bausch & Lomb Spec 20s, the slightly more modern version. Super common for undergraduate labs and high schools. So, here's the plan. We need to choose a wavelength, okay? And then we'll need to set the zero of that wavelength for the sort of background values, the water, any other chemicals that might be in doing that. The way we do that is we need to look at sort of the absorbance profile. How does the substance we're interested in absorb as a function of wavelength? So we're going to go and we put our sample into the spectrophotometer and we measure it at different wavelengths. And we graph it. And we can see this is a made-up profile that I just invented. We can see that this sample absorbs, there's a peak here, a peak here, a peak here. There are different places where it absorbs more light than other places. And that has to do with the shape of the molecule, how it's bonded, the electronic structure, all kinds of different stuff. If we were only concerned with just looking at one molecule, we pick the highest peak. Okay? The high peak, that's where this molecule is going to absorb the best. It means that if I have a solution with a very low concentration, I will still get the strongest signal possible by choosing a wavelength with a high absorbance, where this molecule absorbs light very well. If there's other solutions, other stuff in there, that might change. Michael. Well, there are the array ones are typically spectrophotometers that can measure all the wavelengths at once, or measure a lot of wavelengths at once. That's what you do when you have a whole series of those, because you can shine the light in different pathways, and so you can measure a bunch of different wavelengths at once. And those are typically more advanced machines that you typically see that will do that kind of stuff. So they'll measure a bunch of wavelengths or all the wavelengths in a certain range all at the same time. But they're still a spectrophotometer is designed to measure the intensity of the light, but it could be a combination machine which also measures the spectrum at the same time. Yep, Nikhil. So when you have some sort of background, or you have what we typically call the matrix that our solution is in, all the other stuff that's in there, we might want to go through and measure that absorbance. Okay, so the red line here might represent essentially our background solution. This is sort of everything else that's in the solution at the same time. And what we typically do in this situation is we would look and say, oh, I want a big difference between the background and the stuff I'm trying to measure. So I might choose a different peak, or I might try and modify the reaction so that I have less absorbance in my background. So if it's all by itself, I'm just going to choose the top peak. If there's some background I have to worry about, I want to pick a point, a peak where there's a big difference between the background and the signal I'm actually trying to measure. Okay? So that's typically the way that something like that would work. So if I measure this point here, what I'm going to have to do is I'm going to have to set the 0 point, like the machine, I'm going to set the machine to say, okay, all of this I need to subtract out of my signal. And so what happens is I really only have this much signal that I'm measuring. And the bigger the signal you're measuring is, the lower you can measure, the lower concentration of stuff you can measure. So I have this much difference between the background and the signal I'm trying to measure. And the bigger that difference is, the weaker the signal can be, and you can still detect it above this background measurement. So when you are doing this kind of thing, you need to look for what we call the signal to noise ratio. And that ratio is really going to determine how low can the concentration go before this background absorbance, it will completely overwhelm my signal and I won't be able to measure the concentration. And so the bigger the difference, the lower the concentration can go and you can still measure it. This is definitely a more advanced type of question. It's unlikely that they would do this sort of thing, but it's super important for actual working in a lab. That's why I wanted to bring it up. On the AP test, they typically just show you the one graph and say, hey, what wavelength should we measure? And you say, oh, the highest peak, because that's where the greatest absorbance is, which means my machine will be most sensitive, and I'll be able to measure low concentrations of the chemical I'm trying to find. All right? So, what we're going to be able to do is we're going to be able to make up known solutions, measure their absorbance, plot them on a graph, use that graph of known values to determine the concentration of an unknown sample. That's the primary technique. That's what we need to be able to do for the lab we're going to do on Monday. So tomorrow, we're going to practice all that without worrying too much about chemistry. We're just going to work with some food dyes and measure absorbances on the machine, figure out how we can do concentrations and how the spectrophotometers work in general. Okay, so yeah, we're going to have a worksheet that's going to be a lab where you're going to use the spectrophotometers and measure stuff. On Monday, we're going to be primarily focused on conducting chemical reactions and just using the spectrophotometers to measure the concentrations once we get to the equilibrium. Once we've allowed the reactions to go to become stable and reach equilibrium, then we're going to go ahead and just use the spectrophotometers to measure them. But I want you to have a little familiarity with that so it'll be a little easier to focus on the chemistry instead of the technique of using the spectrophotometer. All right? Okay. So tomorrow, we're going to dive in and start using spectrophotometers.